to undertake these tasks, I'm going to ask you to peruse to a file which you can download from that Google Drive site of which we availed ourselves this morning. So models built-in class. I would like to go to day 1, so preview for exploration day 1. There's a model there called Smoking and Heart Disease Sydney 2017, version 19. Okay. So this is, okay. And I'd like you, sorry. Cancel, yeah. I have to plug this in, sorry. And I'd like you to download that by right-clicking on it and download it, or by double-clicking on it and pressing the download button. Having downloaded it, I'd like you to open it in AnyLogic. Who needs TA help? The TAs, a rump set of TAs remain. I'm not sure where the body has left, but the head remains. So TA, stand ready. Who would like help? Who would like help downloading? Who would like help opening? This model will give us a glimpse of where we're going. Not in all its details. Indeed, it's a model recommended by fulsomeness and richness, but it will lend us a bit of appreciation for our primary quarry at this point, which lies in the central construct of state charts. Tomorrow morning, we'll be backtracking a little bit and seeing where state charts fit in. Fit in terms of delineation of the set of states an agent can be in with respect to a particular concern. The actions by which they can change states, for example, progression of the severity of TB, or occurrence of reactivation of active TB from a latent state, or maybe it's an infection, an initial infection, or maybe it's someone who undergoes natural recovery to an infection, or someone whose chronic disease, say diabetes, develops from a pre-diabetic state to a state of frank type 2 diabetes. Ladies and gentlemen, state charts allow us to encode states they can be in, the actions by which they can change, and the rules under which those actions apply. Now, in this particular model, my voice redounds in a way that is to our disadvantage. In this particular model, if we go look at person here, we'll find a set of state charts characterizing their behavior. A state chart associated with them being divided into their status with respect to their smoking, a never smoker or a current smoker or a former smoker, and status with regards to heart disease, having no heart disease or with active heart disease, whether or not it's diagnosed or not diagnosed. We further characterize with state charts whether they're indeed alive or not, and for certain sake, for whether they're pregnant or not, related to births and in utero exposure to smoking. So we have here state charts, not on one condition, but like Wade's model, we have state charts related to several conditions, to smoking, to heart disease, to vital processes such as death. And of course, these state charts cannot be, and indeed are not, solitudes. heart disease, development of heart disease, what do you think that might be influenced by? Smoking. If someone's a current smoker, it raises their hazard rate, chance per year of developing heart disease, the incidence rate to which they're subject for heart disease. And similarly, heart disease, do you think it affects another state chart, the presence of heart disease? Well, yeah, it might affect, for example, mortality. More than that, it could actually affect smoking status, right? Someone might be more motivated to quit if they discover that they have heart disease. So often state charts are characterizing a particular concern, perhaps a condition or set of factors, but they also interact with other state charts. State charts characterize, for a given concern, the set of possible states someone could be in. Never, current, and former smoker, for example, here with respect to smoking. Those states are mutually exclusive and collectively exhaustive when they're shown as individual so-called simple states. So a given person at any one time is either in the never smoker state or the current smoker state or the former smoker state. But there are these transitions betwixt them by which a person over time, for example, as a former smoker, might relapse back into smoking. Or a never smoker, perhaps through influence of adverse peer companions, might engage in initiation behavior. Or perhaps motivated by incipient heart disease later in life, they might engage in cessation. So we have these states, and we have these actions that move between states. And you'll notice that each of these transitions has associated with it an icon. So there are these funny kind of decreasing curves, it looks like here. Those denote hazard rates, a rate, a chance per unit time, a probability density. I'm using different terms which are used in different. But it's a chance per unit time. It's not a probability, it's a probability per year that they might develop, for example, start smoking. You could think of it as an initiation rate, for example, on an annual basis, or a cessation rate. But these icons can also depict other things. For example, here's an icon that looks like an envelope. That envelope indicates a message transition by which, say, one thing can influence an agent, maybe getting them to engage in a quit smoking program. And they're brought suddenly from being a current smoker to a former smoker by virtue of engaging in an intervention. We can also have timeout transitions by which a person can move from one state to another after a fixed amount of time, or indeed move back to the state. So here we specify some amount of time. We could have it be a constant, say 1 year. Every week there's some action that takes place on from a distribution. So for this person, their latent state lasts 2 days. This other person coming into it, their incidence of disease, it will last 4 days. But it will be after a fixed amount of time, perhaps drawn from a distribution or perhaps a constant, they'll proceed, for example, to another state. So here's an example of this. After 9 months, this individual is leaving the pregnant state and delivering into the non-pregnant state. By contrast, conception, a certain hazard rate. It's a certain chance, time associated with fertility. Okay. So we're going to have state charts like this. And before this day is out, we're going to get our first glimpse of state charts here as built by you. So, ladies and gentlemen, it's only going to take about 15 minutes, but I'm going to ask you once more into the breach. Let us build a little model that has our first state chart, okay? So we're not going to build everything in this model. This model is recommended by a GIS environment centered on the proud city of Sydney here. By its harbor, big enough to hold 1,000 ships of the line. But we will capture some of those essential state charts in our own model, if not all the vibrancy of that pearl of a city. So ladies and gentlemen, I'd like you to go and close this model. As attractive as it might be, you can run it from the comfort of your hotel rooms. And I'd like you to do File, New, Model, and I'm going to say smoking and heart disease. Now, the last model that we built, I argued that time was immaterial. Why was it? What was fundamentally lacking from that model? In a boot camp about dynamic modeling, that model had richness, it had heterogeneity, it had interaction characteristics of an agent. For example, they're dependent on their sex, or we had aspects where their location depended on their income. But what did that model lack? What fundamental thing at the heart of dynamic modeling did it lack? There is no dynamics. There's no change over time. Sure, it captured heterogeneity, but in a static way. We just had this population which had these characters. We showed it in a nice way, and we had interaction, but it wasn't much more than a statistical model in that sense. Here, ladies and gentlemen, you'll get your first glimpse of creating a truly dynamic model. So this yardstick, this meter stick that we're specifying, where 1 means years, is going to have bite to it here. It's going to have significance. It will have, ladies and gentlemen, a measure of gravity. Okay? I'm going to say okay. Okay. So, ladies and gentlemen, here's smoking and heart disease. And just to get us through this really quickly, we're going to create a whirlwind model that will illustrate in a basic way. Before the clock ticks 6, it's going to illustrate state charts and how you can add them and how people change over time their state in response to a state chart. So what we're going to do is we're going to add a person. We want to represent personhood. How do we do that? We add a what? An agent type. And what will that agent type be called? We'll call it person. Here we go. New person, ladies and gentlemen. Person. There we go. And we're going to say finish. How did we do that? I right-clicked on the model, I said new agent type, and I said person, and I said finish. There we go. We have our person. Ladies and gentlemen, for simplicity, I will lend them, once again, the indignity of a circle. The mathematician in me marvels at its fateful symmetry. But for now, it'll have to represent a stylized representation. Tomorrow we'll get into more fulsome representations, anthropomorphic characterizations, sketches of individuals. But here we have it. Person has a little oval associated with them. Okay, let's just rehearse this again. What do we do? Suppose we want to have a population of people. How do we add a population of people? This is personhood we've described in the person class. How do we add a population of people? Where does that live? It lives in Maine, because Maine is the general context, ladies and gentlemen. Now, I've got to be a little bit careful because I still have this simple heterogeneity open. I'm going to close that out black spot so I don't get the two models confused, because then there'll be two mains and we won't remember the main properly. Okay, so ladies and gentlemen, here's person. We'll go to main, and in order to add a population, what do we do? What do we do in main? We want to add a population to it. We need to click and drag person into here. and that will create a population. It will allow us to create a population of people. We drag in. It says, what should the name be? I will say population. And is that all I need to do? Suppose I want a population of size, for example, 100, for example. What do I need to do? Is that a population of people yet? No, we have to say population of agents. Right now it's a single agent. We want a population of agents. By the way, that whispers to us. It whispers to us that we can have embedded agents. We can have agents within agents. We can have city agents, have neighborhood agents within them. Neighborhoods can have schools within. Schools can have children within them. It's intriguing the hierarchies we can have. And before the week is out, we may explore that. But the clock is ticking. So ladies and gentlemen, we have population here. In population, I said population of agents of size 100. We ready for that? Okay. The clock is a-ticking. Next, I would like you to go to that same person, go to population. How do we have those people be distributed at random locations over the landscape? Can anyone tell me? Anyone remind me? Yes, we say specified point. Good, 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 good. So we're going to say in the specified point, and we'll draw it from uniform between 0.0 and 500.0. And we'll do that, in fact, for both x and y. I don't know if you remember that, but not 6 hours thence, we saw that in this very room. Was that indignity first inflicted upon you? Okay? This is what's going in. We say, at the specified point, TAs, let not your wearied muscles prevent you from springing into action to aid individuals who need it. Okay? Okay, so for x and y, we do it at the specified point. What should we see when we run this model now? Run early, run often. We build it. It should build successfully. If it doesn't, a TA, raise your hand and a TA will rush to your side. Now we run it. Now we wish to run it. Boom. Ladies and gentlemen, who needs help? Who needs a TA? TA. TAs, stand proud. Prepare for deployment. Okay, ladies and gentlemen, the clock ticks. All this is familiar territory. We run it, and we see a bunch of agents scattered over. Nothing has changed. It's static still. But now we take our first step into uncharted territory. Ladies and gentlemen, I'd like you to go to person, and I'd like you to go to the palette, and I'd like to add something here that you have not yet added. It's a state chart, ladies and gentlemen, a state chart, okay? And within this state chart, I would like to, I keep on having to redo this. Within the state chart, we're going to drag in first, into person, we're going to describe a theory of smoking. So here we're going to have smoking state chart. Often we have multiple state charts. In this case, we'll have several, heart disease included. So we drag in smoking state chart. We're going to have a state called never smoker. There we go. We have a state called current smoker. And then we have a state, ladies and gentlemen, called ever smoker. Former smoker. Okay. And this provides us we're at the cusp of greatness, ladies and gentlemen. Okay? What we got to do now, we've provided the characterization of states in which a person could be in with respect to this concern. What do we need to do to provide a way of changing states, to undertake an action that changes states? We saw it before, a transition. So we go back to the agent palette or to the state chart palette, either one, agent or state chart palette. They contain the building blocks that we need. And I'd like you to drag in a transition. And we're going to drag it in here to connect these two states. Now, you notice that I through long-time habit, happen to space the states properly. You're unlikely to do so. If you drag in a transition, you're going to want to connect it up. And you have to connect it up so it makes contact with green, okay? And you're going to want to have this upper one. They are directional. They go in a certain direction. I'd like to go to never smoker to current smoker. And I'd like to go from current smoker to former smoker. And then what final transition do we need to complete a quasi-plausible theory? What can happen? Because of the cravings of smoking, what can happen? Is former smoking a final state for most smokers? Alas, they can fall back due to the addictive powers of nicotine. So we've just hitched them up like this. How did I do that? I dragged in some transitions, and I hitched them up. I hitched them up to dock with this, and they turned green at their ends. I connected them like that. Make sure both ends are green, so they're connected. Green is the color, and state charts are the game. Okay, we're all in this together, and modeling is our game. Okay, so we're connecting these up. Okay, ladies and gentlemen, now we have associated each person with a theory of smoking. Let's run the model. First of all, let's build it. TA, stand firm, stand ready, stand poised. Okay, build the model and see if it build completed successfully. Who needs TA help? Okay, TA help. Sector 2, row 1. Others? TA help. TA help? Okay, ladies and gentlemen, let's run it. Let's run this model. What do we see? I'd like to try running it. It's not obvious what's going on. Let's go down to the level of a population, ladies and gentlemen. Do you see what I see? What do you see going on? What apparition lies before you? What happened in your model? Sorry? So TA, sector 1. Ladies and gentlemen, I just went down. So ladies and gentlemen, you need to go here. Remember, we can dive down to the level of individual with this navigation menu. Remember that? We dove down. And here we go, alternating between former smoker and never smoker. What's going on? This person is engaged in quitting, and then what? They fall back into their habit. Ladies and gentlemen, we've engaged in dynamics. Not yet realistic dynamics, but dynamics nonetheless. Sorry? Yes, they're in a loop here. Now, ladies and gentlemen, to illuminate this better, I'd ask you, we have 5 minutes remaining before my promise. We already have achieved dynamics. I've met my promise, but I want to add just 2 or 3 additional things here. Ladies and gentlemen, if you could go to the agent, and I'd like to add into the model, for the first time, a variable, ladies and gentlemen, a variable. That variable will be called, where did I go? I went to the agent palette, and I dragged in a variable to person. And that variable is going to be called color, C-O-L-O-U-R, in honor of the Queen's English, spoken by many of those in the room. But we will face the ugly prospect of having to deal with the dictates of the American Imperium for other things. So we have to abide by the spelling choices of our southern neighbor for certain things of which we cannot choose. So ladies and gentlemen, this is color. Do you think color is a double precision value? No. Is it an integer? No. Is it a Boolean? No. Is it a sex? Most definitely not. So what is this thing? Well, it's an other, and in fact, it's of type color with a capital C. That denotes the set of all possible colors, just like sex with a capital S denoted the set of all possible sexes, or person with a capital P denotes personhood, the set of all possible persons. Here, this is a set of all possible colors. It's with a C, and it's spelled according to American standards. Color. And its initial value, ladies and gentlemen, will be black, as in Conrad, who served as a guest, he reported, of the United States government for many years. He said he was domiciled as a guest of the U.S. government. In other words, he was in prison in the U.S. Formerly Lord Black, knighted. Okay, ladies and gentlemen, we have black in color. So what did I do? I added in a variable. I called it color, spelled according to Queen's English, and I then said its type is other. It's color according to American standards, because we can't choose how to phrase this. Colors in AnyLogic are Java colors, and that came from the U.S. And initial value is black. Okay? So we have people as a black color. Where do you think we're going to use the color? Can anyone speak? Okay, we'll use it up here in the oval. We're going to use it for the fill color. Ladies and gentlemen, how do we make fill color be something that we don't just pick it from the list? We want to specify a rule for it, a formula for it. How are we going to specify that? How do we type it in? If we start typing here, it's not going to be happy. It's going to ignore us. How do I type it? Anyone remember? Yeah, we have to click this. We change it to dynamic, and I'll say this dot color. Hey, my color. It's my color. Whatever my color is in that variable, change it to this. Sorry. And it's my. That's why this dot color. My color. Whatever it is, make that my fill color. Okay? Time is a ticking. Ladies and gentlemen, I'd like you to build the model. TA stand ready in this final advance. Okay? Okay, ladies and gentlemen, I built and it succeeded. I'd like you to run this now. Since it succeeded, we can run it. There we see black. Black as Conrad himself. Okay? Okay, ladies and gentlemen, one final thing here that will highlight for us the heinous nature of the current dynamics. I would like you to click on one of these states. You'll notice for each of the states you can specify what's called an entry action. That specifies when I go into that state, what do I do? And I'm going to change the color. I'm going to assign to this very variable that we added an appropriate color. So coming into this never smoker state, I'm going to say this dot color equals, not double equals. Double equals mean we're testing whether it is equal to something. Here, we're assigning it to be the color green. Actually, I'll say lime. Okay, lime green. This dot color equals lime. Meaning we're assigning this variable. So when they come in here, what color will they change to, do you think, visually? Green is the color, indeed. Okay, for current smoker, we're going to set it, this dot color equals red. By the way, I'm cheating a little bit. I'm copying and pasting. This dot color equals red. Make sure it's color spelled according to the Queen's English, because that's the name of the variable, ladies and gentlemen. Here we set it to be lime. Here we set it to be red. And here we set it to be gray. Okay? I built. So, ladies and gentlemen, never smoker, this stock color, my color is lime. Ladies and gentlemen, for current smoker, my color is red. For former smoker, my color, ladies and gentlemen, lies gray. Can we run it? Let's build, make sure it's all hunky-dory, and we're going to say run here. There we go. Do you see something unsettling? What's going on? In grim succession, they're going back and forth. Ladies and gentlemen, there's dynamics going on, but it's dynamics of a singularly monolithic character, is it not? So let us break free of that tyranny. Let us introduce here an alternative transition. Instead of having quitting be based on a timeout, right now it's a timeout. That means after 1 year of becoming a smoker, they're going to quit. And indeed, after 1 year of being a former smoker, exactly, they're going to relapse. Instead, ladies and gentlemen, I'm going to change this to be a rate transition. I'm going to call it quitting. Here, I'm going to call this transition quitting. I'm going to tell it to show the name. Yeah, show the name, and I'm going to click on this little thing and drag it down. Show the name, and I'm going to say they quit 3 times per year on average. They make a strong quitting attempt. The actual statistics are quite telling. If you look at some of the surveys, there's actually a lot of quit attempts. And the sad thing is people fall back often quite frequently. Next, for former, so let's run that. What do you think? Do you think everyone will pulse? This is a hazard rate. It's a hazard rate of 2.0 per year. It's a probability density, a chance per unit time that they will quit. Some people may quit sooner, some people later. But this is a chance per year that associated with probability per year. It's not a probability. It's bigger than 1 after all. But it's a probability per year. What that means is, on average, twice a year, they're going to quit. If it were 10 times a year, equally much so, on average, it'll be 1/10 of a year between quit attempts. If it's 2.0, it'll be 1/2 of a year, 1/2, between quit attempts. So let's run this thing. Now we run it. What do we see now? Are they all in heinous synchrony? No longer in synchrony, ladies and gentlemen. I'll slow it down so you can admire its variegated character. Gerard Manley Hopkins wrote in praise of mottled things. You'll notice that this matches his description. Agents are engaged in smoking. Some have quit and are therefore gray. The red ones are smoking. Over time, there's a certain hazard rate, a chance per unit time. They'll quit. This one just quit. Sometimes they'll fall back into smoking. Okay, here we've seen ways we can characterize dynamics with a state chart at an individual level. We've seen how different types of transitions to specify logic, say an incidence rate for developing a disease, for example, might be a rate transition or a certain chance per unit time of quitting. We could have this return one rather than having them automatically fall back into smoking after a year. Maybe we'll set this relapse transition to be a rate transition. You'll notice the little icon changed. A timeout was this little clock icon, and here we'll change it to be a rate icon, and we'll set it to 4.0 per year. In other words, there's an average of 1/4 of a year, 1/4 years before they're the average time until they fall back into smoking. And we could run that again. And here, not only will their quitting time be variable, but their relapse time, ladies and gentlemen. So here they're engaged in pulsing, And if we go down and look at each individual, we can see the different states they're in. And in fact, it's printing out how long it will be until they're smoking, or until they quit. Here, we didn't show the name associated with this. I didn't even give it a proper name. I'll say relapse, and I'll say show name, and drag that up there. And this, ladies and gentlemen, will be a transition called initiation, okay? And I'll set that at a hazard rate of let's say, 0.05. So maybe I'll do 0.010. So on average, 0.01. So on average, it will take them 10 years to initiate smoking. Now, we're going to play a lot with state charts in this boot camp, but this shouldn't obscure the fact that state charts characterize a set of possible states. A state chart, a given state chart, is with respect to a certain condition or a certain concern. A state chart characterizes the possible states they could be in with respect to that concern in a way that's mutually exclusive and collectively exhaustive. Transitions between the states describes actions by which an agent might switch from one state to another. For example, initiating smoking or quitting smoking or relapsing smoking. There's a logic to the connections and their relationships to the states that transcends any particular data. Here, what this is saying is, once someone leaves the never smoker state, they can never get back to it. Once they've left the never smoker state, they can either be a current smoker or former smoker, but there's a certain logic they can't get back to a never smoker state, right? There's no reverse transition. And no matter what parameter values I have, it's going to capture that fundamental regularity. This is what I mean about we put elements of theory into models, how we characterize things in their relationships. Here we saw that if we use certain types of transitions, we get certain behavior. The first transitions we used were the default ones. They were timeout transitions. That meant after some fixed time, we definitely leave the state. And there was time to one. And so they moved in heinous synchrony from one state to the next, from this state to this state back, to this state back. Remember them blinking at us in that horrible way? But now they're desynchronized because we just have a chance per unit time, and some go sooner and some go later in terms of moving. As we'll see tomorrow, we can even have the probability, say, of relapsing depend how long they've been quit. Maybe they've been quit for 5 years. Maybe they have a very low chance of relapse. Each successive, they feel less in the way of craving. Their social circle is expanded more than their smoking friends, and they're less likely per year to fall back. We can capture that in this framework, as it turns out. Time-varying rates with some finesse. We'll also examine situations where one agent influences another, maybe through peer pressure or situations of direct transmission of norms, attitudes, beliefs, or indeed pathogen. Those are different types of transitions, and you can see as you pick down a transition, you can specify a timeout, which we saw before, a condition, a message, or in fact, I can transition it. I can ask to transition one state to another when I arrive at a destination in terms of mobility. Okay? So I proceed to the and once there, I engage in some sort of behavior. I go in a state of, under care or something like that. Ladies and gentlemen, this is a state chart. It's a state chart, and a state chart is a fundamental building block that characterizes possible states of an agent with respect to a concern, actions that change those states, and rules under which rates or timeouts, rules under which those actions apply. And that is the final building block we're adding to our models today. Okay, one final, ladies and gentlemen. I have provided to you, provided us with in this boot camp a set of possible project ideas as suggested by the surveys that came in. I will confess that I was trying to infer, okay, who might be suggesting what. It says project ideas. I will send you this link here, but I would invite people to fill in additional ideas for projects because I'd like to get started on those projects. Not today, I think we've had a full enough day, but tomorrow morning. And I'll be talking about some help for that on the project conceptualization side. But we have a set of 4 projects that were suggested: case management and youth recidivism. I guess that might be you, Terry? No? Oh, who? Oh, awesome. Well, that sounds like a joint. That sounds really interesting, and it might be of interest to you, actually, to see that. And then explore use of ABM, impacts of food environment on childhood obesity prevalence in low-income kids. And I think you would also suggest examine feedbacks between feeling busy, that is low levels of discretionary time, stress, and present versus future time preferences, which is really interesting. I have no problem with suggesting 2 projects if you're not averse to having different students explore each of them in conjunction with you, and you can circulate. Yeah. 1,000 flowers bloom. Okay, UTIs in a residential setting, determinant prevalence, cause of hospital presentations, and linked to antimicrobial. Awesome. Awesome. Okay. So I misinterpreted. So let's get this down here. So this is actually not Terry, but remind me the name. Yeah, Tenny. Okay. And these I inferred correctly. Again, a clock is right twice a day. And then the UTIs, Megan McStay. Okay. Awesome. And tomorrow morning, we're going to try to kick these off. I have rooms devoted to where we can explore these throughout the boot camp. Rather than trying to change rooms every time and have a musical chairs, I figured we'd try to have designated rooms for each of these. But I'd invite you tonight. I'm going to send you a link to this, which you can fill in. And if some of you are interested in some of these projects, like joining in, you can do so. If you want to propose new projects, please do so by tonight so that we could rustle up some TAs and deliver on them with a passel of a model. So I'll send you the link to this, and we'll see if we can, by tomorrow morning, pick which project, make sure we have some space, and get TAs going with some early exercises to work towards a model. Okay? So that's the plan. I want to thank you so much for your questions today, for your tolerance of the lapses, but also for your curiosity and speaking up with some excellent questions. I really feel that the level of discussion in this boot camp is actually above most I've participated in, and I'm really grateful. Maybe it's been tops of any I've been in, and I'm grateful to you for speaking out and raising questions. If there are ways we could further improve the boot camp experience for you, please let me know. But otherwise, I will look forward to seeing you tomorrow morning in this room at 8:30 for some new forays into the world of dynamic modeling. Thank you very much.